So welcome all to week 6 tutorial for the course Deep Learning. I'm Pintu Kumar. I'm a PhD scholar at IIT Bombay. The topics that I intend to cover today is autoencoders. So uh, the discussion would be slightly brief than what we have been doing in past. So I'll talk about architecture of autoencoder. Okay, and then I'll move to some of the regularization technique for autoencoders. Then something that I have planned for today is I'll discuss a PyTorch implementation of autoencoder. Okay, so I won't be explicitly calculating the backpropagation and I won't be using it in my code either. I'll be going with a PyTorch implementation for autoencoder that you people can use to practice. Okay. So one thing that I would say right now, this PyTorch implementation right now is not at all perfect. I purposely sort of not chosen the best learning rates and those kind of things. Okay, so I'll just give you an idea how an autoencoder architecture can be written by PyTorch and would expect you guys to hypertune the model, try changing the hidden dimension and those kind of things and see how does your result vary. So those things you can do. Okay, so we'll try to cover this in first 1 hour of the lecture, and next whatever time is left with us, we'll try to go for the code. Okay. Okay. So generally, whenever we talk about autoencoders, the architecture that should come to our mind is something like this. So what we do, we begin with some large dimensional input, and we keep decreasing the dimension of intermediate layers. So these are the hidden layers, and we try to keep on decreasing the intermediate layers, and we reach something that is known as bottleneck. Okay. So this bottleneck is also known as feature. So this is generally, we call it of dimension D, and here onwards we again keep on increasing the dimension back to the original dimension of the data Rn. Okay. So the main goal of these kind of architecture is to able to regenerate the input from the lower dimension feature. Okay, so first of all we convert some n dimensional feature to d dimensional feature, and then we try to recreate our initial input that we had from d dimensional feature to n dimensional feature. Okay, so like roughly speaking, it is like compressing your n dimensional data into d dimensional data, because if you are not able to compress your data properly, you won't be able to regenerate your data back to your n dimensional data. Okay, so yeah. Okay, so there is as I said, today I'm gonna not go into a lot of discussion. So there is something known as undercomplete and overcomplete autoencoders. You can divide autoencoders into two parts. One is undercomplete, another one is overcomplete. So an undercomplete autoencoder looks something like what we just sort of discussed. So we have some higher dimensional. Okay, so I'm not drawing all the connections. You know how a multi-layer perceptron looks, right? Okay, let me draw this side, and yeah, then there is a connection from here to here. Okay, so the hidden feature dimension that we sort of obtain, this d, and let's say if my input dimension was n, and n is less than, sorry, and if your d is less than n, that is the dimension of the hidden feature is less than n, then this sort of autoencoder is called undercomplete autoencoder. Okay, and if it is the other way around, then it is known as overcomplete autoencoder. So let's say you have 3 inputs, and in the hidden feature you obtained 5 inputs, then you again got back to 3 inputs. let's say there is some connection from here to here, then from here to here. Okay. So this kind of model would be known as overcomplete autoencoder. Okay. Here obviously your D is greater than equal to N. Okay. So this is the difference between overcomplete and undercomplete autoencoders. Now, whenever we talk about neural network, what things do we need to decide? Okay, so let's say you have some application, you want to make a deep learning model for that. What are the things that you need to decide? Okay, so first thing that you need to decide is the architecture. Okay. Okay. So how many hidden layers you want to choose? So what is the dimension of your hidden layers? Okay. So these things you need to decide. Next thing that you need to decide is what should be the activation functions for your neurons. Okay. So it can be same activation function throughout, or you can have different activation for different layers. Even you can have in some very complex applications different activation function for sort of neurons in same layer, but that would increase the complexity. Somebody has some questions? Okay, which one is under and which one is over? So under is the one in which your dimension of this hidden feature is less than the original dimension. So this is under. And the one in which your hidden dimension has more number of neurons, or its dimension is more, is over complete autoencoder. Okay. So third thing that you need to decide is the loss function that you want to choose. Okay. So in general, when you have autoencoders, what you want is, I'll just copy this thing here to here. So what you want is, let's say this is X is your input, right? If X is your input, this is X1, X2, okay? And this is your, let's say X hat 1, X hat 2. What you want your X1 to be equal to uh, X1 hat, right? So architecture we have already taken care of. What we want is, we want either it should be decreasing towards the bottleneck, or it can increase towards the bottleneck in case of overcomplete. But let's assume that it is decreasing. Architecture we have decided. Next thing that we want to decide is the activation function that we should select. Okay. So for activation function, what we want is that the input should be same as the output, right? So So what does this motivate us to do is, so whatever is the nature of your input, okay, whatever is the nature of our input, we want the activation function for the last layer of the neural network that we are designing to output values of same nature. Okay, so let's say if your x belongs to some Rn, so x1, x2, x3s are your some arbitrary real number. Okay, so what you want? You want that your x1 hat, x2 hat, all these things should also be arbitrary real numbers. Okay, so you can sort of make two cases here based on this assumption. Let's say if your input is some arbitrary real number, then what should be a good choice for activation function for the last layer? So if your input is arbitrary real, then activation function for last layer can be linear activation. Okay, because linear activation gives you values from minus infinity to infinity, right? So this can be a very good choice for the last layer activation. And for the other activations, that again depends on your application, but sigmoid, people have used sigmoid and it gives good result. You can also use ReLU. This also gives good result. But for the last layer, you should try to stick to linear activation function. Okay, you can have other activation function also which gives values in this range, that is from minus infinity to infinity. That again will depend a lot on your application that you're working with. Okay, now many applications are there in which the input itself is a binary input. That is, you have only values between you have values 0 and 1, or you can assume that you have values between 0 to 1. Okay, so here also we can have linear activation. Okay, but even better activation choice is something that we learned, that is logistic activation, right? Because logistic activation gives you values between 0 and 1 only, and that too it has a very flat portion that is towards the 1. So if you remember, the graph looks something like this, if I remember correctly. Yeah, so there is a large value that has value 0, there is a large portion that has value close to 1. So that's why this is a good choice for this kind of autoencoder. Okay, any doubt till this point?
Sir,
Yes.
in case of input, if input neurons are different from output layer neurons, in that case, we cannot call it as autoencoder, isn't it? Am I right?
Yes, because in autoencoder what we want is that the output layer should match with the input layer.
Okay, fine. Okay, sir. Okay. Thank you.
So yeah, moving ahead, we talked about three necessary ingredients that we need to create a neural network. And we have talked about architecture, we have talked about activation function. The next thing is the loss function that we should have. Okay, so what we want is, we want that my x and x hat should be close to each other, right? Again, we can divide this based on the type of input that we have. If input again is some arbitrary real, okay, then what is the best choice that we have? The best is, you look at the difference.
Linear.
So linear is our activation function. Now we are talking about the loss function.
Okay,
So
sir.
this is the squared error that we can have,
Square. Okay.
right? So this is one very good choice that we have. And if we have, let's say, some extra characteristic involved with our input, so let's say if our input is binary, so here also you can use mean squared error, that is, you can again use this error. But even a better error would be your cross entropy loss that we learned. Okay, because your values are between 0 and 1, and you can treat it as a kind of probability if you have used logistic activation in last layer. So you can further use cross entropy loss. Okay, so this was something like MPI log of Qi, right, where Pi was your true distribution. So if we write in terms of x and xi hat, so this would be xi and this would be xi hat. Okay, because this is our predicted value. Okay, so this is a very brief introduction to autoencoders, like how we can create an autoencoder, what kind of activation functions we should use, what can be the loss function possible, and those kind of things. So let's try to solve some question that were there in previous year's assignment. These might be similar to what you have to do this year. Okay. So the first question is, which of the following network represents autoencoder? Okay. So the only thumb rule for autoencoder is that your input should match with the output, right?
Third one, sir.
Yeah, third
C.
one is correct because the input size over here is same as the output size over here. For other examples, you'll see the length of input and output varies. Okay. Yeah. So next question is, which of the following statement is true regard to overfitting in overcomplete autoencoder? Okay. So yeah, one thing that we didn't talk about, we will talk about. So what is the phenomena of overfitting? Like anybody who has done the machine learning course would definitely know this, but I'll just sort of revise very briefly. So whenever we train on some training data, okay, if you choose a complex model, okay, what happens is your model memorizes data. So like when you were child in your school also, there would be many kids who would understand some pattern behind some question, or they would understand some logic behind some question and then attempt some question, right? And then there would be some other students who might have very good memory power. They would memorize all the questions, and when it is asked in the exam, they'll write it as it is. But if you give those kids questions that are slightly different from what they have memorized, it becomes very difficult for them to produce good answer over there. Okay. So similar is the case with overfitting. So in case when model memorizes data and do not learn pattern in the data, it becomes difficult for it, okay, for it to do good on unseen data. So it becomes difficult for it to do good on unseen questions. But the whole goal of this machine learning or deep learning is to learn some pattern from data, and when you encounter some real world unseen data, you should be able to make some prediction based on whatever you have learned. Okay. So how does an over complete autoencoder look like? Let's say I have two input and I have 3 or 4 neurons in the hidden and 2 output. Okay, something like this. Okay, so I think like if some connections are missing, you can, yeah, this one is missing. Yeah. Okay. So if this is your network and your goal is like if this is x1 x2, you want this x1 had to be equal to x2 x1 and x2 had equal to x2. So what you can do is you can just give weight 1 to this one and probably weight 1 to this and 0 everywhere else, right? And similarly you can give weight 1 to this thing because from here to here we want this, and from here to here you can give weight 1 and rest everything 0. So this is just sort of identity map. You don't even need these things. So if you look at this, this is sort of memorizing the data. It will give you 0 error on the training data set. Okay. And it will memorize the data. So when you give it some new, let's say x1 star, x2 star, it won't give you very good features. The features wouldn't be that great for you. Okay. So this is one problem that we encounter with the over complete autoencoders. Okay. So it is asking which of the following statement is true with regard to overfitting in over complete autoencoders. First option is reconstruction error is very low while training. So this fact is correct. We just saw like if we just assign 1 weights over here and 0 everywhere else, it can memorize every data point and it can give 0 training error. Okay. So first option is correct. So network fails to learn good representation of the inputs. That's what I said. So the representation that it would be learning would be again x1 and x2, and that won't be very good, right? So this one is also true. Third one is network learns good representation. This is false. Reconstruction error is very high while training is again false. So first two options are correct and last two are incorrect. Okay, this question you guys can answer. You can type it in the chat box. So the question is, suppose for one data point we have features like this, -2, 12, 4.2, 7.6 and 0. Then which of the following should we use on the output layer of the decoder? Okay, so which activation function? So which following activation function I should write? So which of the following activation function should we use on the output layer of the decoder? So what do you guys feel? Right. So yeah, D is correct. So we want a linear activation function so that it can give values, even negative values, positive values and zero values. Okay. Okay, so this question is, if the dimension of hidden layer representation is more than the dimension of input layer, what kind of autoencoder do we have? I think this year you have a question where you have is more is replaced by less. You can correctly answer this. Yeah, C is correct answer. This is called as overcomplete autoencoder. This is just that we saw. Okay. Next question is, which of the following is the potential advantage of using overcomplete autoencoder? Okay. So overcomplete autoencoder have this problem whatever we discussed. What can be a potential advantage of using like overcomplete autoencoders? Okay. So one way, like how you can avoid this identity map in overcomplete autoencoder is via regularization that we are going to do. Okay. So you can do regularization even for undercomplete autoencoder, but it becomes more useful for overcomplete autoencoder. Okay. So one thing that this your overcomplete autoencoder can do is it can learn more complex and nonlinear representations. Okay. So like if you will have an undercomplete sort of autoencoder, its more focus would be on compression of data. And if you have a regularized overcomplete autoencoder, it can learn more complex and nonlinear representations for you. Okay, so this is one good. So reduction of risk of overfitting, we know that it overfits, so this option is incorrect. Faster training time, the training time actually would be more than the undercomplete one because you have more number of weights to learn, so the training time would be more. So last option is to compress input data. So to compress input data, you use your undercomplete autoencoder. So this option is also incorrect. Any doubt till this point? Then we will look at some regularization technique for autoencoders. Okay. So anybody who has done a machine learning course, can you explain option? Why option? Definitely, I'll explain. Okay. So the first option says it reduces the risk of overfitting. Okay. But just now we discussed, like if you have an overcomplete autoencoder, it will memorize, it is very easy for it to memorize every training point. That's why it sort of overfits. So that's why it actually does not reduces the risk of overfitting, but it will definitely overfit to the training data. Okay. Okay. So I hope Namana was clear. So let's get to regularization in autoencoders. So anybody who has done a machine learning course would be aware that this is a best way to, I won't say best way, but a very easiest and common way to regularize. So why sort of we overfit, that actually is in next week, but I'll sort of try to motivate you. Okay. So what we actually do is, like in any machine learning or any deep learning algorithm, you have some data point, let's say xi comma yi, right? There are a bunch of these data points that you have. So there would be some underlying true function for which your f of xi was equal to yi. So if you have some data, let's say xi comma yi, then these data points were generated from somewhere. Okay, so let's say there was some function f by which this data point was generated. Okay, and the problem is that we don't know this function. Like, this is just basic stuff that I'm repeating, but it would be useful. We don't know what is f. This is the whole problem of machine learning and deep learning that we have been doing for 4-5 weeks, right? Now what we try to do is we try to estimate this f by some f star, and we want f of xi to be close enough to yi, or we want this f of xi to be close enough to the original f of xi. Okay, and when it is not equal, we calculate error and do all those kind of things, and then we try to optimize. Okay, now what happens? Yeah, the screen is shared. Is it visible to other? That would have been a blunder if it wasn't shared. You can try rejoining. That might be useful for you. Okay, right. So this is what we hope for. Okay. Now, whenever we collect data or we generate data, there are many sources of error that can creep in. Okay, so let's say if there was some true distribution or true function that could have given us exact xi comma yi, whenever we obtain data, there can be like we don't have many experts to generate those kind of data. There can be several reasons. Just assume that there can be some error in the data that we have generated. Okay, just remember this thing. So what happens is, let's say we start searching our f. Okay, so there is one thing that is known as hypothesis class. So what does hypothesis class represent? So hypothesis class is set of all functions in which we will search our f star. Okay, for example, if you are looking at some linear classifier, then your hypothesis class is set of all linear functions. Okay, so when you go to deep learning, your hypothesis class increases and it becomes set of all non-linear functions. So we did some universal approximation theorem where we learned that this f star can approximate any smooth continuous function, those kind of things. So we can search over a very large set of functions. But as I mentioned, the data set that we have available with us is slightly noisy. Okay, now let's say if we allow f star to search over all the possible functions, then it will definitely produce some function f star, so that the error on training is 0. Okay, error on training is 0. But what we actually wanted is, we wanted this error on true data set to be 0, not on the noisy data set to be 0. Okay, so what we do is we restrict the search space, restrict search space so we just restrict the search space of f star so that it does not exactly fit this noisy data set. Okay, this is what we want. So this regularization, when we say regularization is nothing but trying to restrict the search space of our function so that it does not exactly fit the training data set, and it does equally well on, hopefully it does equally well on the test data set that we encounter in future. Okay, so this is what is something that is known as regularization. So first technique for regularization is something that you might have done. This is known as L2 regularization. Okay. So what is the idea behind L2 regularization is, so if let's say you had some loss function L theta to begin with, so you define some loss function. This can be squared error, okay, this can be cross entropy, and whatever you can define, like that's up to you. Okay, now you define a modified loss function L hat theta, which is your original loss function plus some lambda times norm square of your all the okay, so this should be theta. So thetas are all your parameters that you have. Okay, so all the weights and biases together forms your theta. So you put it in a vector and take the norm of that particular vector and add it to your loss function. So what it does, so it won't allow you, I should change the color because here also it is 0. So it won't allow large value of theta. So because you are not allowing large value of theta, now what has happened? So you have restricted your search space to a smaller space where your theta values are small. Okay. So yeah, this is one method for regularization. And this again, your lambda is some hyperparameter that you can tune. Okay. Any doubt in L2 regularization? Okay. So next thing is, so okay, I'll again copy this figure. I'll paste it here. That figure is slightly useful. Okay. So let's say this weights that we are having on this side, we represent it by W, and the weights that we have on this decoder side, we represent it by W star. Okay. Now let's say my W and W star don't have any relation among them. So this not equal to does not mean that they are not equal, but I am representing that they don't have any relation among them. Okay. So this is one thing. Next thing, consider a sort of a class of a function. So f of x is given by ax plus b. Okay. And f star x is some ax. Okay. Now in the above example, you have two like coefficients that you can choose, right? You can fix your a and b and generate set of functions of this type. Here you have only one choice, that you can only fix a. Okay. Now in the above case, if you take b is equal to 0, you would be able to generate all the functions of form f star x is equal to ax. So we can sort of say that the functions that are generated by a function of form f star x is a subset of functions generated by f of x. Okay. So if you have more number of weights, if you have more number of biases to tune, that means you are sort of generating a more complex function. Okay. More complex function, that's why you have a more larger search space. Okay. So if you can reduce your number of weights that you want to learn, that means you are reducing the complexity of your model. That's why you are incorporating some sort of regularization in your model. Okay. So in this method, what we do is we fix W star to be W transpose. Okay. So this weight over here would be same as this weight over here. Okay. This weight over here would be same as this weight over here. Then the number of elements in hidden layers also become same. So the encoder part is sort of a replica of decoder part, and we have lesser number of weights to learn. Okay. So this is also a sort of regularization. This I think is known as tying up the weight, right? Any doubt in this part? Like, why does this regularizes? What is the idea behind it? Any doubt? So we'll just, sir, theta is the norm after complete training. No, no, no. Okay. So this loss function that you will define will be for every, will be at every step of the training. Okay. So what will happen when you will initialize your theta, let's say, okay, I'll use some other place. So how you begin training, you initialize some theta. At that point only, the loss function that you will define would be L of theta plus norm of theta square, some lambda over here, right? Now you will find the gradient of this complete function and take one update step, and then you will reach from, let's say, theta to theta 1. Okay. Then your loss function will get modified to L theta 1 plus lambda theta. So this term would be included every step of your optimization. So it won't be after complete training, but it will be involved in training. That's how you will be able to regularize. Om Prakash, was I clear? Okay. Okay. So this is a sort of I would say regularization technique only, but this also is quite common otherwise also. This is something known as denoising autoencoders. Okay. So what is the idea behind this denoising autoencoder is, so what I said is, let's say you have some initial data point, true data distribution. Let's say this is some true data distribution D star. Star means true. Okay. But what you have obtained is some xi tilde, yi tilde belonging to some d tilde. Okay. So this is what you have obtained. Now we didn't want it to fit to this xi tilde comma yi tilde, but we wanted to fit to the original xi comma yi. Okay. Now what this denoised autoencoder proposes is, it says whatever data point you have obtained, you add some noise to that particular data point and obtain xi tilde. Okay. And then pass this xi tilde via autoencoder and try to regenerate xi hat. So what we are trying to do is, we are trying to generate xi from noisy data set. So this sort of also helps you denoise your data point. Okay. So the motivation behind this is just this much, that your data set that you obtain is slightly noisy. So why not first add some noise to your data set and then train your model so that it can regenerate xi on its own. Okay. So this is the idea. So this P can have different models. It can have, let's say, uh, if you had some xi comma yi, so to your xi you added some standard normal distribution. So you generated a number between 0 to 1 using, so you generated a normal distribution number with mean 0 and standard deviation 1, and you just added to xi, and you trained your autoencoder on this, right? But remember, what is your ultimate goal? Your ultimate goal is that your xi cap should be equal to xi and not xi tilde. So you want your output layer to be same as xi and not your xi tilde. Okay. You are giving it input and noisy thing, but you expect and clean data set out of it. Okay. So this is another sort of regularization technique. Why is this a regularization technique? Because this was your training data set and it is not fitting to this particular training data set, because the input that we are providing to autoencoder is something different, that we have noised our set and it is able to produce something that it has not seen at all. Okay, so that's why it is sort of a regularization. Okay, so we have questions related to all this sort of autoencoders that I have included towards the end. We'll cover those. Okay, so there are two more left. Yeah, any doubt in the previous portion? Then we'll go to sparse autoencoder. I'm sort of skipping the proofs and everything. The reason I mentioned in the beginning, we'll try to look at some code today. Okay, so we are saving time for that. So something that is known as sparse autoencoder. Okay, so what does sparse autoencoder say? So sparse term is not only true for autoencoders, but it is true for any neural network in general. So there are sparse neural network also. Okay, so what happens in sparse architecture is you don't want your neurons to always fire. Okay, so what I mean by always fire, that you don't want your neurons to give value 1 most of the time. So what you want is, let's say it should fire only 1 by 100 of time. Okay, so if it would have fired at some arbitrary points, that would have meant that you are able to search in a larger space, right? Now if you have restricted that 90% or 95% of the time you should output value 0 only, for every neuron you have made this kind of restriction, that means the kind of functions that these can generate are more restricted. Okay, so there is also one advantage of using these kind of sparse neurons. The advantage is whenever they will fire with some important features. Whenever they will see some important features, then only they will fire, because eventually we would be decreasing the loss between xi hat and x cap. So there is one condition that will say that you shouldn't fire a lot many number of times, and there would be another condition that would want xi to be close to xi hat. So it will try to optimize a combination of these. So what will happen in this process is, the only way xi can reach xi hat is that these neurons should pick important features from xi, and at those particular instances only it should fire. Okay, so yeah, so this PL, let's say this is my neuron L, then this rho L represents the number of times my neuron has fired. So this is fraction of time my neuron has fired, and we want it to be very close to 0. Let's say we want it to be 0.005. Okay, so what we want is that my rho L should be equal to rho. Okay, so the way we regularized our in case of L2 regularization, we do similar kind of regularization over here also. So our loss is modified by, so we have some original loss that we can pick, plus some sigma of theta. What is this sigma of theta? This will ensure that my rho L is as close as possible to rho. So if you see, this rho L is a fraction, or you can say it is the probability of a neuron firing, right? So what is the best way you can compare to probability is something known as cross entropy that we have done in previous classes. So this sigma of theta is nothing but cross entropy between this rho L and rho. So you can have something like this is minus of rho log rho cap L plus, I think it should be minus over here, yeah, plus 1 minus rho, and then again log of I think this is what we can do. This is one possible way. There is one more possible way that I think professor has covered. You can check that also. I think there is some fraction also that he has involved. So you just need to ensure that your rho L and rho are close to each other. Okay, so this is another way of regularizing your autoencoders. Okay, so last one that we have is something known as contractive autoencoders. Okay, so first of all, I would define something that is known as Jacobian. Okay, so you learned about gradient. Okay, what was gradient? So if you have f, a function of let's say x, y, z, and you wanted to find the derivative of, so this was represented by something like this. So what was the component? It was derivative of f with respect to x, then derivative of f with respect to y, derivative of f with respect to z. This was your gradient, right? Now let's say, so what was f? F was a function from R3 to R. Okay. Now let's say you have some function g, which is a function from Rn to Rk. Okay. These kind of functions do exist, right? Let's say there is some function from Rn to Rk. How do we define something similar to gradient for this case? That term is called as Jacobian. So if this is a function from Rn to Rk, then g would look something like, so there would be some g1, which is a function of x1, x2 to xn. Then there would be some g2 till gk, right? So this would look something like this. So here my h is a function of x1, x2, xn. Okay, so this is del h1 by del xn. So first row is the gradient of h1 with respect to your x. Okay, so this is del h1 by del x1, del h1 by del x2, and so on. Again, second row is del h2 by del x1, and so on. So the last element over here you can see as del hk by del x1. This is something that is known as Jacobian. Okay. So another term that you see over here is Frobenius norm. So this is norm of a matrix. Okay, so let's say this is norm of a matrix is defined as summation of I from 1 to n, j from 1 to m, aij square. So you take sum of, so you square all the entries of your matrix and then add them up. That gives you your Frobenius norm for your matrix. Okay. So what is contractive autoencoder? So contractive and autoencoders include this Jacobian term as a regularization thing. Okay. So how does this sort of regularizes? So what we actually wanted is that if you go to this initial discussion that we had on regularization, where did we had? Yeah, here. What we said is that to the original data that we have, what we do is we add some kind of noise, right? So this noise generally won't be very large, right? This noise would be some very small quantity, let's say modeled from normal distribution with zero mean and one variance or those kind of things. So let's say if we want something like, if I perturb my data xi comma yi by some small amount, or if I perturb my data a little bit, then the output should not change. If I'm able to find this kind of function, so that if I perturb my data a little bit and my output do not change, then I'm able to sort of regularize my model, right? Because this is what my problem was. When my data was getting perturbed a little bit, the function that would fit would drastically change. But what I want now is, if I perturb my data a little bit, the function should not change a lot. Okay, so this is what we are imposing via this Jacobian norm. Okay, because we are sort of trying to minimize this thing. What does this mean? We are trying to minimize each and every of these quantities. So we are trying to minimize the change in the like the features that we would get if we change our x1 a little bit, the change in feature that we would get if we change our x2 a little bit. So we want to minimize this thing. So features that we are sort of learning would be robust to these perturbations. Okay, so this is one way to view this thing, why we add this kind of autoencoder, add this kind of regularization. Another thing is that, let's say this L theta term was missing. Okay. And let's say this term was missing and we had only this second term with us. Okay. What would it do? If we want to minimize this thing, what would it try to do is, it will try to find a feature that it will try to find the intermediate feature that we have. The autoencoders come something like this, and then we have some bottleneck in the middle, right? So what will it try to do is, even if we change our data, okay, the feature won't change. So what it will do is, for any input you give, it will output the same feature. But this is not what we want, right? We want to learn also something out of it. That's why we take a combination of both these things, that we want to minimize the loss also, and we don't want this thing to perturb a lot also. Okay. So what it will eventually do is, it will pick only important variations. Okay, so it will pick only those features x1, x2, xn, perturbing which gives a lot of advantage to L theta. Other features, it will try to push its gradient to its derivative to 0. Okay, so one thing to remember is, this contractive autoencoders picks important variations similar to PCA. So PCA also used to pick those directions which had important variations, where variation was large, and similarly this contractive autoencoder does similar thing. Okay. Okay. So any doubt in this? Okay, so we'll try to solve some questions based on all these regularizations that we have done. So let's look at the first question. What does this say? Which of the following statement is true with respect to regularization in autoencoder? Okay, so it is asking which of the following statement is always true with respect to regularization in autoencoders. So what do you think? Which ones should we take? Okay, so the question was, which of them is always true? Okay, so regularization shrinks the size of weight vectors learned. This is not always true. Okay, there are other methods that we discussed uh, for which we didn't reduce the size of vector. We reduce the size only when we tie W star with W transpose. Okay, so like from understanding perspective, there are some regularization method that also does this, but here we won't take this option. Second is, regularization reduces the search space of weight vector. This is correct, right? Because it will reduce the search space. Whenever we are imposing any extra condition, it will lead to reduce in search space of weights of the network. Regularization help reduces overfitting. That's also correct. That's the whole purpose of why we are doing regularization. We don't want to overfit to the data. Okay. So B and C are correct option according to me. Okay. Okay. Let's look at this question. We are given an autoencoder A. The average activation value of neurons in this network is 0.001. So this is a row that is given to you. Okay. What kind of autoencoder it is? Okay. So we just now did, this is a sparse autoencoder because we don't want neurons to fire always.
Sir, if it is 0.06?
I think that is this year's question. But see, what does 0.001 mean? So if you look at the, just a second. If you look at this definition of row, what is this row defined? So this is number of times your a particular neuron would fire on an average. Okay, So if this value is, let's say over here 0.001, and let's say your m is 1000, that means your this summation is only equal to 1. So out of 1000 data points, this has fired only for one data point. That's why we are calling it sparse. Now you said some other value. So let's say if it has fired for 10 out of let's say 1000, still it's sparse, right? Even if it has sort of fired for 100 out of 1000, still it is sparse. So you can think that way. I can't tell you the exact answer because it is in this year's question, but you can think it that way. If the number of times which it has sort of fired, then it is a sparse. So anything sort of below, let's say 0.1, you can sort of go that it is an sparse autoencoder. Okay. Okay. The next question is, what is the primary objective of sparse autoencoder that distinguishes it from vanilla autoencoder? Okay. So which option do you think is correct for this question? So what is the primary objective of sparse autoencoder? So somebody says C. Okay. Learn a low dimensional representation of the input data. They minimize the reconstruction error between the. So C is correct because they will go only for the important features. Variation might not be very useful term over here, but they will only go for important features. Whenever they will fire for some important features. Okay. Next question is, what is or are the primary advantages of autoencoders over PCA? Okay, so you remember PCA also did data compression, and when we are having autoencoder of this form, where you have hidden representation of lesser dimension, then also you are doing data compression only. Okay, so it is asking what are the advantages of autoencoder over PCA. Okay, so let's see what options it has given. Autoencoders are less prone to overfitting. Okay, um, so what do you think? Is autoencoder less prone to overfitting than PCA? Okay, let's look at second question. Autoencoders are faster and more efficient than PCA. It is definitely not faster than PCA because you require training over here. In PCA, you just calculate the matrix X transpose X and you have SVD and everything. It's very much mathematical and much faster than autoencoder. Okay. Autoencoder requires fewer input data than PCA. This is also not correct. Autoencoder can capture non-linear relationship between data. This option is correct. Okay. The only advantage that autoencoder has is that it can capture non-linear relationship in the input data. Okay. Okay. Let's look at the other way around. Okay. So which of the following are potential disadvantages of autoencoder for dimensionality detection over PCA? So they are asking about what are the possible disadvantages of autoencoder now. Okay, let's see what options are here. So first option says autoencoders are computationally expensive and may require more training data than PCA. This is definitely correct. We discussed it in last option. Autoencoders are bad at capturing complex relationship in data. This is incorrect. It is good at capturing complex relationship. Autoencoders may overfit the training data and generalize poorly on new data. This is also correct. Autoencoders are unable to handle linear relationships. This is not at all applicable. Okay. Okay, so we are done with this portion. Now we will go for the code, right? We'll try to see a sort of basic code for this autoencoder. So I'll give you a 5-minute break, right? So that yeah, I'll give you a 5-minute break, and we'll discuss this code at 7:10 probably. Okay, so this is a 2-hour long lecture. So we will take a 5-minute break, and then we'll discuss this code on autoencoder. So this is using PyTorch, and pretty simple code that you can try and experiment with. Okay, so you um okay, I'll just so you want the final exam paper or the assignments that I'm discussing?
No, sir, previous year papers or model papers which we can solve as a reference.
Okay, so I don't think those are available. We also don't have any access to them. Also, I won't recommend you solving them, because generally there would be some TA. So this is IIT Roper score, TA at IIT Roper who would create paper this year, and that TA need not be same as previous year. Okay, so the questions are very much likely to be different. So there is no use of also looking for those kind of papers.
Okay, sir. Thank you, sir.
Okay. Okay, we can start discussing the code. Okay, so again, the rules are same. If at any point you don't understand any line in the code, just stop me then and there. Okay, and I'll try to clarify. So this is sort of a easy code. I'll try to explain. Okay, one problem is that I can't write on it, but that's fine. Okay, so I'm using this PyTorch library. So the first line is import torch. So PyTorch is a very common library these days, which helps you make deep learning model very easily. So it takes care of your back propagation, forward pass, everything it takes care of. Okay. So second thing that I have imported is torch vision. So I would be implementing it for your MNIST data set, and that data set is available in this torch vision library. So I'm using this. Next thing is I'm importing something known as transforms. What would this transform do is, transform would convert your image data set to a tensor data set data. Okay, so you have arrays, and similarly it will convert your images to tensor. Next thing that I am importing over here is something that is known as matplotlib.py plot. I am importing it as PLT. So what would this do? This would help you view your image. Okay, so view your MNIST images. Okay, I also want to use the GPU capabilities that is available on Google Colab. So I'm defining something as device. So device will have value CUDA if GPU is available on my device. If it is not available, it will go with CPU. Okay, and the last library that I'm importing is this is TQDM library. If you have done Python, you might be aware. So what it is, I'll tell you later. This is very simple thing. Okay, so I'm starting to run this code. Okay, so generally, if you speak mathematically, arrays are two-dimensional. Tensor are more than two-dimensional also is allowed. But if you talk in terms of Python, so there are two different libraries. One is called NumPy. So NumPy uses arrays. So you can only work with arrays if you are using some NumPy function. And this PyTorch or TensorFlow uses tensor when you are trying to use functions that are defined in PyTorch or TensorFlow. So this is a major difference that you can see. Okay. Okay. So here I'm trying to, so this is tensor transform that I said. So what I'm using from transform is that I'll just convert whatever it is to tensor. Okay. And here I am downloading the MNIST dataset and saving it in my root directory. Okay. So I'm just saving it over here. I want to train it. If it is not available on my device, then download it. This download equal to true means this. And whenever you have downloaded the data set, then transform it using whatever I have defined as tensor transform, that is convert everything to tensor. Okay. What does this loader do? So can we get multi-dimensional arrays? Yeah, mathematically it is just different naming, but from implementation point of view, if you are using PyTorch, you should go for tensors. Like they have a framework known as tensors. If you are using NumPy, you should go to arrays. So you can have a NumPy array which is three-dimensional. You can have a PyTorch tensor which is just a single value or a one-dimensional, so vector kind of thing also. Okay. Okay, so what does this loader does? So you might remember we discussed something known as gradient descent, batch gradient descent and stochastic gradient descent. Right now I'm implementing batch gradient descent with batch size of 512. Okay, so I'll compute gradient for 512 images at a time, update my gradient again for the next 512 and so on. This is how I'll do. Okay, so this is what has been done till now. So I'm downloading my data and that data is getting saved as data set. Okay, so let's see how does a image in this data set looks. So I am outputting, let's say 45th image of this data set. So plt.im show, that is image show, would output something like this. So this image is a 9 that I'm outputting, that I have outputted for you. Okay. Now this is main thing where your PyTorch comes into picture. This is a class of autoencoder that you are defining. Okay. So what you are doing, you are defining something that is known as self.encoder. So what will happen in encoder? These things will work in sequential manner. So what will happen? You begin with an image of 28 cross 28. So this is the dimension of your input. That input is mapped to 128 dimension by linear transformation. Okay. On that linear transformation, you apply ReLU. Okay. So I am using ReLU activation function in the hidden layers, not in the output layers. Okay. Again, I am converting 128 to 64, then 64 to 36, 36 to 18, and then 18 to 9. Okay, this is the conversion that I am doing. So I have gone from 784 dimension to 9 dimension. This is my encoder part. Now for the decoder part, I begin with 9, I go to 18, then 18 to 36, 36 to 64, 64 to 128, and then finally 128 to 784. I have defined my encoder part and I have defined my decoder part. Now I need to define something that is known as forward pass. So when you define forward, you need to mention if an data point enters your this class, how would it pass? Okay, so when it enters, it should first go through encoder. So you have x, you pass x through encoder, and you receive something that is known as encoded. Then you pass this encoded to receive decoded, and finally output or return decoded. This is what your autoencoder does, right? Okay, so we have defined such a class which will do these kind of things for you. Okay, now let's create a data point. I shouldn't call it data point. Let's create a variable model of this class. So I created a model named a model named model of class AE. Okay, and I have converted my model to device. So just ignore this line for the time being. What I am doing is I am pushing this model to my GPU so that my calculation becomes faster. This is the only purpose of this model to device. Okay, now I am defining a loss function that I should be using. Loss function that I have defined is torch.nn.mean squared error loss. Okay, the final output layer is sigmoid, and I have defined mean squared error loss. I could have defined cross entropy loss also. Okay, just remember that. And again, I am using Adam optimizer that we have discussed. So I have defined optimizer is equal to torch.optim.adam. You need not worry a lot about it. You just need to specify your learning rate and decay rate, and your optimizer is ready. Okay, so just a recap, what all things we have done till now. We have downloaded the dataset. We have defined a class of autoencoder which contained encoder part and decoder part, and a forward function which tells you how your input variable should flow. Then we defined a variable named model of this type autoencoder. We have defined something that is loss function and optimizer. Okay, here is where your training would go. Okay, so till which point I had ran. Okay, so I'll run this code also. And here is where your training starts. So backprop is backpropagation. So we'll do backprop over here now, right? So we have just done the forward pass here. While training, we will do the backpropagation. Okay. Now see what happens over here. This is number of epochs. Number of one epoch means when you have exhausted all your data points. Okay, so one iteration would mean you have picked 512 data points. Okay, and you have updated your weight. This is one iteration. Then you will pick the next 512 data points. This is second iteration. When you are exhausted with all your data points once, that would be one epoch, and I'm training it for 20 epochs. Okay, so this TQDM that I didn't mention in the beginning, this is TQDM. What does this TQDM does is this will generate this kind of green box that will tell you how many epochs you have ran. So if you include it in for loop, it just gives you a bar that would progress slowly. That you will see when we'll run this block of code. That would run slowly and tell you like how much process has been done. Okay. Okay. So we created a loader over here of batch size 512. So now here we will just run in loader. So we are loading images from loader. Okay, now the images that we had, okay, so I didn't show it over here, but the images that we had is of size 28 cross 28. Okay, but when we pass it through neural network, what we want to pass it in size 784 into 1. So we want one layer of size 784. So this is what is happening over here. We are reshaping it into size whatever is this is -1, you can ignore. This is 784 cross 1. So this is 28 into 28. This is not 28 cross 28. So this won't form a two-dimensional vector, but a one-dimensional vector that will be formed. And again, two device you can ignore. Two device is just to push it onto your GPU. Okay. So now I pass this image that I have obtained via my model. So whenever I have written this thing, reconstructed is equal to model image, what will this PyTorch do? It will automatically create a graph where it would know that this weight now is being used to calculate this reconstructed. When I then pass this reconstructed and image into loss function to calculate loss, okay, and then I do a loss dot backward step. I'll come to this step in a while. I'll tell you what it is. But what we do is we do a back propagation, loss dot backward. So if I write loss dot backward, my PyTorch will do a back propagation on its own. Okay, because it has created a graph on its own when I wrote these two lines, reconstructed equal to model image and loss equal to loss function. Okay, and then I'll take an optimizer dot step. What will it do is it will take one step in the direction of your gradient. This would do a gradient calculation. This will do one step in that direction. Okay, now what is this optimizer dot zero grad? So PyTorch has a special property. So let's say if you calculated your gradient for 512 points, and if you don't include this line, that is optimizer dot zero grad, next time if you will run this loop, so it will obtain your gradient for another 512 points and add it to the previous gradient that you have obtained. This is a property of your PyTorch. Okay, so it is useful when you will do RNN and those kind of things. But right now what we want is you calculate for 512 points and make your existing gradient to be 0. Again calculate for 512 points. Now it will add to the previous value, but previous value we have already made 0 over here. Okay, that's why we are using this optimizer dot zero grad to make the previous value 0, so that your update is based only on the current gradient values that you have. Okay, so here we have take a step, we are saving losses over here. Okay, and we are saving outputs also. Okay, let's start the training and let's see what happens. Okay, so we have started the training. So we are doing it for 20 epochs. See, the one epoch got finished in 7 seconds when we were using GPU. I can try towards the end showing you how much time it would take if you would have used CPUs. But yeah, so we are training for 20 epoch, let's say. It will take some time. Right? We don't have much left to do. We have trained our autoencoders. We just need to see the input and output. Here I have tried to plot the loss of last 100 iterations, just to check whether my loss is still decreasing or not decreasing and what is happening. If you see that loss is sort of fluctuating, that means either it is stuck somewhere or it has sort of reached where it should have reached. Otherwise, you should have been gradually decreasing when your iteration is decreasing. Sorry, iteration is increasing. So let this model train. It will take 1 more minute. So this was the role of TQDM, that it will just give you a progress bar that will keep telling you how much epochs have been completed. So because this epoch was to run in range 1 to 20, so it is telling you 14 epochs are done out of 20. Okay. It also tells you how many seconds it is taking for iterations. So in how many seconds it is performing one epoch, how much time, expected time is left. This is not always accurate, but it gives you an idea how much time is left for the run. You can use TQDM for these purposes. Okay, so the training is done. We can sort of try to plot the loss. Loss would look similar. Yeah, so loss is similar. Now I'll try to print some original image and the regenerated image. So what happens in autoencoder? You have some original input and you have some output layer, right? So let's see how the output looks. So the generated image looks. So right now what I have obtained So these are same, but the values that I obtained are not very same. This is what I told you when I was like telling you that I'll show you the code. So we can try some other image also. This is the fourth image from the data set. Let's see how does this look. This looks something like one. And how does this fourth image look for the reconstructed one? This again is very similar to what we obtained in the. So there are few reasons why this thing is happening like this that you need to figure out. So till this point, this gives you an idea how you can write an autoencoder code with PyTorch. So what things I haven't done and want you guys to do is, so you see that I converted 784 to 9 layers. Okay. The question is this 9 layers good enough to capture this kind of features? Okay. Is this the reason why we are not getting very good generated image? One question is this. Okay. Another question is, how can you include regularization in this? So I would give you the answer. You would modify this loss function to get regularization. Another thing that I hinted you is that there is this torch nn dot sigmoid, right? And I have used mean square error loss. Whereas when we discussed, I said that we can also use cross entropy loss. Okay. So you guys can try all these different kind of combination. You can play with the learning rate and see what kind of values do you get and what kind of optimized value do you obtain. Okay. So I'll upload this code. Okay, so that you can play around with it. I have purposely not tuned it so that you guys can get an hands-on experience how to tune it. Okay. Also, one more thing that I would mention is the best way to sort of learn Python, at least for deep learning, is these libraries keep getting updated almost every 3 or 4 months. Okay. So the only way that you can learn it through is its documentation. Okay. For example, let's say I have this loss function as toss dot mean square error dot mean square error loss. Now I want to replace it via let's say cross entropy loss. How would I replace? You just type on the Google cross entropy loss PyTorch, right? It will give you the exact like library where it is present. So for example, this mean square error loss was present in torch.nn folder. So you can use that thing. It will also give you the parameters that you should input, right? Because that is also important, right? What kind of input you should give to your loss function. Okay. So these things you should explore with this code, and this is the only way like you can get some hands-on experience on this deep learning model. Okay, like this torch.optim.adam. So what is this learning rate? What is this weight decay? Everything is mentioned in the documentation of PyTorch that you can explore. Okay. So yeah, this is the code that I had. Like any doubt that you guys have at any line, I would be happy to explain. I'll upload this code as well as whatever I scribble as soon as this class gets over. I think you know from where to access these files. So yeah, you guys can try with this code. I definitely you can ask it in the next class also. I'll possibly try to save some time towards the end for this thing, because this is how you will sort of learn doing deep learning